Welcome back. This is Mrs. Edwards, and today we are going to be evaluating limits using the algebraic method. But before we get to the new method, I want to just quickly go over the methods that we've covered so far. We want to find the limit as x approaches c of some function, and if we were given a graph of that function, we learned a kind of lazy way to determine the limit. If you happen to see a break at the x value or an asymptote at the x value you're getting close to, or the x value that you are located is at an endpoint, well then the limit does not exist. This is not a formal definition. This is just a real quick and easy way of making the determination, but not an official justification. Also, if we see that at the x value we're getting close to, we see a hole, or we see that the curve is smooth there, the limit does exist. But then we still have to figure out what is the limit there. So the general idea is you want to find the intended height from the left and from the right. And if those are heading to the same height, well, then the height that you get to from both sides is the answer to the limit. The next method, you were given an equation of f of x rather than f of x's graph. So we would make a table, and we would create a table that was centered around the x value that we are getting closer and closer to. So in this case, that would be c. Then we begin selecting x values that are getting closer and closer to c from the left side and the right side, plugging those numbers into the function and looking for a pattern of answers. If the answers keep getting closer and closer to the same number, then that is the answer to our limit. This is a way to approximate the answer to a limit. We did find a shortcut that occasionally cut out having to make the table. In general, you do not want to think of just substituting a number into the function to find the limit. However, if you substitute in the number, sometimes it is equivalent to the limit, and that happens whenever you substitute the number and you get out a real number. The catch still is as long as the function isn't a piecewise function or you are not at an endpoint. Then we had a method that worked for both, for looking at a graph and also looking at the equation of f of x. And that was the formal definition. This is the definition that you need to know for the AP exam. And so if you were asked to justify your answer to the limit on the AP exam, you need to know these three pieces. You have to state that the limit as x approaches the number you're getting close to from the left of the function exists, and you do that by simply finding out that it equals a real number. And then the limit as x approaches a from the right exists, and again, that is just finding the limit from the right, and it is a real number. And then step 3, that both the limit from the left is equal to the limit on the right. Okay, now for method number 4, let's find the limit as x approaches a number using an algebraic method. I want to remind you, on the AP exam, you will not have your calculator for all parts of the exam. So it's important that you can find the limits algebraically, because you won't be able to just pick up your calculator and use a table or look at the graph. So here we go. The first step in evaluating a limit algebraically is what I call plug and chug. In other words, you're just going to substitute the number you're getting close to and then simplify. Substituting in 3 into 2x plus 4, simplifying, I get 10. 10 is the answer to this limit. You will only need to do step 1 if, when you make the substitution, you get out a real number. This is similar to the shortcut that we used in the table. I'm going to do another example, however, that illustrates how it's just a tiny bit different. Finding this limit, I start with step 1, substituting 3 into the function x plus 2 over x minus 3. I simplify and I end up getting 5 over 0. This is not a real number, but we can say in the algebraic method that if you get a number over 0, then the answer to the limit is does not exist. Let's look at a third example just to make sure you don't confuse does not exist with the number 0. If I find the limit as x approaches 3 of this function, starting with step 1, I just substitute in 3, but this time when I simplify, I get 0 divided by negative 2. 0 divided by negative 2 equals 0. 0 is a number on the number line, so the answer to this limit is 0. For each problem that you are using the algebraic method, you will always start with step 1. You're going to substitute in the number. So now let's look at a problem that step 1 is not enough and we have to have a step 2. Starting this problem by substituting in 1 and simplifying, we get 0 over 0. 0 over 0 is an indeterminate form. This does not equal 0. So if you substitute and you get 0 over 0, then you need to factor, cancel, and substitute. When I factor the numerator x squared minus 1, I get x plus 1 times x minus 1. I cancel, and now I have the limit as x approaches 1 of x plus 1. So we've factored, canceled, and now I will resubstitute the 1 into what's left there and simplify again, and we have 2. So the intended height from the left and the right as we get close to 1, it's heading to a height of 2. Just a note about what y equals x squared minus 1 over x minus 1 would look like. It would just be a line y equals x plus 1. But there would be a hole in the line at 1, and that's why we ended up getting 0 over 0. Canceling removes the hole, and then we get to the line without the hole, y equals x plus 1. Evaluating this limit using the algebraic method, we'll begin using step 1, which is just substitute in the number 4. Plug and chug. I substitute, I simplify, and I get 0 over 0. Darn it, more work. So we're going to have to move on to step 2 when that happens. In step 2, you would like to factor, cancel, resubstitute. When you're looking at that, you're thinking, well, that doesn't really look like I can factor that in the traditional sense. So that's what takes us to step 3. We have 0 over 0. We tried to factor and we couldn't because we see a square root. So step 3, what you want to do is you want to multiply the numerator and denominator by the conjugate of the piece that has the root in it, because we want to get rid of the square root. You learned about conjugates in Algebra 2. So just very quickly, a conjugate, if I had x plus 2, then it would be x minus 2. If you had 3x plus 4, it'd be 3x minus 4. You're just changing the sign in the middle from positive to negative or negative to positive. So to multiply by the conjugate of root x minus 2, I'm going to multiply by root x plus 2. Now when I multiply these two fractions together, multiplying the numerators together and the denominators together, do not multiply the denominators together. The reason that you don't want to multiply the denominators together is because ultimately what we want to happen is in the end something will finally cancel. And so we want that denominator in factored form. We are multiplying the numerators together because the purpose is to get rid of this root. All right, so FOIL together the numerators, first times first, outer, inner, last. And when you do that, you're going to end up with x plus 4 in the x minus 4 in the numerator. Voila, pretty cool. Check it out. X minus 4 is now in the numerator and the denominator, so we can cancel it. And so to finish step 3, now that we've got this to factor in a roundabout sort of way and cancel, now we can resubstitute. So I'm going to substitute in the 4, simplify, and the answer to this limit is 1/4. You now need to go to part 2 of this lesson so that you know how to handle absolute value functions.